Good evening, Arun here, sir.
Good evening. How are you doing?
Sir. Yes. We will wait another 5 minutes, sir, because
Sure.
participant. Okay, sir. Arun sir, shall we start, sir?
Yeah, I'm ready.
Okay, sir. Good evening to all. Welcome the resource person Arun Iyer for the today's session. Welcome you, sir.
Thank you.
And also I welcome convener Dr. Praveen J, sir, for the today's session. Welcome you, Praveen, sir. And also I welcome all the participants for the today's session. I request Arun Iyer, sir, to carry the session.
Okay, may I start presenting?
Yes, sir. We can start.
Okay, thank you. Okay, I just started sharing my screen. Let me know when you all can see it.
Yes, sir. It's visible, sir.
Okay, great. So, so we spent time on discussing combinational logic and some of its aspects yesterday. We're going to continue discussing sequential logic today. This is the agenda for today. I have, as usual, just like yesterday, we have 2 breaks. And so we're going to spend the first 45 minutes covering the topics here. And between break 1 and break 2, we're going to cover some of the topics shown here. And what I'm going to do today is I'm going to bring up a specific paper which talks about comparing various flip-flop topologies. I'll go over that paper. It's a very interesting paper. It's very well read by people who are interested in understanding about sequential elements, the timing aspects, how to design them, optimize them, and so on. So I'll spend not a lot of time, but maybe 5 to 10 minutes on it. I'll try to show how to read the paper, how to understand various aspects of it. Before we get into the paper, I will show some specific sequential element topologies, the circuit styles, and compare them so that we are prepared to, or will be in a shape to understand what this paper talks about. And then you can probably go on your own and read the paper. And if you have any questions, maybe we can discuss that. Maybe you can send the questions to the organizers, or we can probably discuss that on the last day when we can probably have longer Q&A sessions, right? I wanted to cover characterization today, but there's a fair amount of material here, and I thought it probably wouldn't do a good amount of justice in explaining it to the audience if these things are not covered properly. So I have split up the characterization part and moved it to tomorrow, and we'll come to that, and we can have a more detailed time we can spend on characterization and optimization and other system level timing aspects. So sequential elements, understanding why they're required, how they're designed, the timing aspects is one of the most fundamental aspects for digital design. And we'll spend a good amount of time today. Okay, so let's get started. So we covered combinational circuits yesterday, and this is sort of a very simplistic view of it. So you have a black box where you could have some function, let's say f, and you have a set of inputs coming into it, and then based on some states of these inputs or some arrangement, some combinations, whatever you want to call it, there will be a set of outputs, right? This is usually sort of well known to us, right? This is something which is fairly common. We see this in a lot of places. Now, this is sort of like we call it like a unidirectional flow of information. So you have inputs coming in, you have the inputs being processed in a function, which could be a black box. You may know the internals of it, but maybe for some other people, they may not know what's inside, but they just see the inputs they're providing, and you get some sort of outputs. So, but in real life, you rarely see such systems, or complex systems usually are not like this. Complex systems, or which basically what most of our real life systems are, could be biological systems, physical systems, chemical systems, any kind of system that there is always some sort of a dependence on the history or the previous value of the outputs, right? So which means there is something from the output which goes back to the input, either directly at the same level as the inputs coming in, or some part of the some intermediate stage of the processing happening inside the block. But if it's a black box, I mean, it could be just coming in, and so which means that this view is obviously not very practical. Real systems are not like this, right? Now, this feedback from the output back to input is something which all of us fairly, I mean, see it fairly commonly, right? And that's basically the motivation for bringing in sequencing or sequential logic here. So as I said, you just have combinational inputs here, but a real complex and a more or interesting systems obviously require some awareness of what happened to the output at a specific point in time. We can use them, update the system, tune it, or calculate the outputs in some other way based on some previous states, and so on, right? This is how, in reality, a physical system or a complex system would look like. So as before, external inputs. So here we are calling it external inputs to distinguish it from the output which has been generated earlier. So external inputs, external outputs, and then we have output fed back to the input, and there is some functional block called a memory element. And to distinguish between whether output was generated recently or in the past, we are calling it, giving it a name, next state or current state. You can use any terminology here, right? This is how a complex system would look like. There's a feedback here from the output back to the input. Now, if we just continue talking about this system, which has a feedback from the output back to its input. So does the memory element, as shown here, require any special characteristics or controls? Right? What does that mean? So people who are seeing this for the first time, I mean, they probably may not understand or appreciate what I'm trying to ask here, but people who already studied digital logic or who spent some time looking at digital systems obviously would clearly get the flow of what I'm trying to talk about here, right? So let's sort of continue building upon it. So what I'm asking is there something special about these memory elements, or there's no real requirement about how they need to behave or how they need to act on the inputs, and is there any specific requirements that they need to meet? That's what I'm asking. So let's see. Okay, just a minute. I think the update is happening slowly. Okay, sorry about that. So if we continue with the discussion, so let's just say that I have taken this generic system like this, and I have actually put some logic inside this, some combinational logic, and I also brought in some sort of a feedback as shown here. Right now, to show something representing this memory element. I put this yellow block here just to show that there's something like called a memory element, or something which represents the memory element as in this diagram, in this specific circuit or logical diagram that you have here, right? So if the memory element is a simple wire, so which means it is just it just means that this value y, small y, is same as the output y, which is sort of feeding back, right? So this circuit can certainly use the previous results or values of y, and it meets the requirements as shown in this type of complex digital system. But do we see any challenges? Do you see any problems with this kind of a system? Can you type into the chat? Do you see any concerns? Do we see any challenges in this system? Am I audible?
Yes, sir. You're audible.
Okay, so I'm asking to the audience, do you see any challenges in this system where this yellow blocks is just a simple wire, where the small y is directly, there's nothing but the value y here? Do you see any challenges? Challenges in terms of, in terms of building the system? So someone is asking challenge in terms of what, and I'm saying challenge in terms of what? My challenge, the question I'm asking is, when I say challenge, I mean the problem. If the system is as simple, where this yellow blocks is just a piece of wire, and the memory system is just a piece of wire, and the value of y is directly updating the value of small y. See any concerns here?
So about the delay constraints, where delay becomes more.
Delay becomes?
The delay becomes more, no, sir?
Delay becomes more. Why does delay become more?
Because it is waiting for the output, because the output is one of the input for the gate, no, sir?
Output is one of the inputs, you're saying?
Yes, sir. The Y is also the input to the gate, no, sir?
So what? That's fine, right? You can assume some value of y, and you can do the calculation, and the y changes, and then it comes back and updates the small y and changes again, and so on, right? So what's the problem there?
Sir, if x2 is 0, irrespective of the value, always output will be 0.
If x, which one is 0?
x2 is 0 means?
Can you please can you speak slightly slower?
Sir, if x2 0,
x2 is 0, okay?
output is always 0.
So that's okay, right? And if x2 is 0, that's how the functionality of this logic is. So that's something which, let's say, some customer or someone has written it. I don't know. It's beyond me, right? And he's built it this way. When normally, if x2 is fixed as 0, you don't need to put a function for that. But this is which the fact that someone has used an AND gate and x2 is here means x2 will not always be 0. So it may be changing. So that's fine. That's not a problem. So someone says, Anirudh says, during initial condition, y is not known. Okay, so let's say we make an assumption about y, and will that solve the problem? Okay, Sanjay says, there is no stable output. Sanjay, can you unmute yourself and let's talk about that. Why do you say there's no stable output?
Yes, sir, because due to delays between the two gates, the output may vary, sir.
Output will vary. You want output to vary, but what's the problem with if when you say there's no stable output, what do you mean by that? I mean, basically you're on the right track. So when we say you're on the right, when we say the output is not stable, I think if we qualify it better, what's going to happen is, let's talk about it. I think Dr. Nagesh says race.
Since it
So
is a combinational circuit, sir. So there will be continuous change to the input stimulus, sir.
So it is not combinational anymore because there is a feedback here. So it's not a combinational circuit anymore. There is some memory here. There is some previous dependence. So it's not combinational. That's clear because combinational is only dependent on one set of inputs and outputs. But this one is dependent on its past, right? So there is a dependence. It's not combinational. But the interesting thing is that
Output is not locked, sir, actually.
Output is not
Locked.
logged. What does that mean? What do you mean by that? So let's sort of discuss this more. So now the problem is that if this is just a wire, I think we can certainly build it like this. What's going to happen is a wire obviously is just a small conducting element, right? And which means there is the delay, the resistance of a wire is very small, which means delay from Y to this small y is nearly zero, right? Almost instantaneous. So which means as soon as this changes, and Y is immediately going back and trying to update itself. And this keeps repeating. Keeps repeating, and which means there's a potential that this whole thing just keeps oscillating. Depending on the value of x1 and x2, the initial conditions, let's say on x1, x2, they are coming from output, so we can set some values here. So which means this is just toggling back and forth, and so on. Now, if you want to build an oscillator, I mean, that's okay. But I assume when you're building something, a circuit which looks like this, it's not supposed to be an oscillator, then there's a problem, right? So there is a problem, and this is what's called as a race. Okay, sorry, I think the update is taking slow. Okay, this is called as a race. What's a race? The race is that this value of y, the new value of y, is coming in and trying to overwrite the previous value of y, which was updated on the small y, and immediately coming in and trying to change the values here, right? And now what it means is that you need some kind of a sequencing. Some kind of sequencing in the sense that the value of the new value of y should come in and update the old value only when we want it to be updated. So this sequencing or this sort of controlled operation is needed here. And so this sequencing is something which is something which is a real practical requirement when you start building sequential circuits or sequential elements. Yes, we need a memory element, we need a feedback, but the memory element needs to have some special characteristics. It needs to be properly sequencing things. And that's the first thing we need to know when you're building a sequential circuit. So now, if let's say we understood that this sequencing is required, I assume this is now clear that there will be this problem of oscillation or a race which keeps happening, and we need to sequence, right? I assume everyone got that, right? If you did not, maybe we can talk about it during the break and try to discuss it in more detail because it's an important concept. But we'll continue. And one way of sequencing this is by introducing some kind of a special signal. What's one sort of a very crude way of sequencing is that I can add a significantly large amount of delay. If I go back to this previous if I go back to this previous slide, so this, I can add a significantly large delay. What should be the large delay? That large delay should be such that it is significantly greater than the delay from Y to Y. So if I can add a significantly large delay, which is many times more than this delay, then what's going to happen is I can retain the value of Y for a sufficiently long time. And even though it comes back and tries to write into Y, it is sort of delayed by that huge delay that I'm adding here. And this whole update of Y is now delayed, and Y is going to be stable for a longer time. And then after a delay is covered, Y comes in, updates Y, and a new update happens by traveling through this logic function, and Y gets updated, and the whole thing keeps updating, keeps repeating. This again doesn't completely solve the oscillation problem, but the point is that this allows Y to be stable for a longer time, and you can clearly see what will be the relationship between Y and Y when you can add a lot of delay. And that's something which is a very crude way of doing it, and something which certainly can does a form of sequencing, but that's not usually recommended. Why? Because it is very dependent on the kind of logic or the circuit that you have here. The amount of delay you need to add is never fixed, because these circuits are dependent on how they are manufactured, what sort of voltage they have, how fast they are. So there are too many variables to determine what the delay you need to add. So therefore, even though the delay may partly solve the problem, it's something which is not recommended and not done by anyone in the industry, or even in general. This is not recommended. So you can certainly run simulation for a long time and do that, but and test it out, but it's not something which is done in general by people who are building complex systems. So the best approach, or one of the better approaches is to introduce an additional signal. Let's give it a name C standing for control. So some control signal C, which what it can do is sequencing when Y is updating the small y. So when C is equal to 1, this is a digital signal, a Boolean signal. So when C is equal to 1, you allow small y to be updated by Y. Otherwise, C is blocking Y, and therefore Y is still holding on to its old value. Right? Sort of like an if-else statement, right? If C is equal to 1, small y is equal to Y, else Y cannot flow through, which means this Y is Y. What do you think? Does this solve the race problem? Can you type it in the chat? Does this solve the race problem? Can we discuss this in the chat? Does this solve the race problem?
Sir, what about the propagation delay of the gates? Gate will be having propagation delay, no, sir?
So we'll talk about our propagation delay, but do you think this is solving the race problem?
Yes, sir. Yes.
It solves? Okay. And others in the audience, do you think this is solved? The race problem by doing this? Okay, a lot of you say yes. Let's see if it really solves the race problem or not. Now, we did this, we introduced this signal. Does it solve the race problem? Yes, but only partly. Why partly? Because it solves, so let's say C is a digital signal which can go high and low. And because it's a control signal, it may go high and it may go low. And you could probably have it coming in at some specific rate. So it solves the problem for the period when C is low, C is equal to 0. But when C is equal to 1, you still seem to have the same problem where this thing is just like a wire and Y is still continuously getting updated. If that's what you want and you want to block only for a small period of time, then you could have just used that big, large delay as we discussed. Or, I mean, if you're okay with this approach, yes, go ahead and use this. But if, let's say, you still have concerns that Y is coming in and immediately updating the value of small y when C is equal to 1, then this does not completely solve the problem. We still have a race, but maybe 50% of the time we have a race when the period when C is equal to 1. So what are the approaches that now that we have to fix this problem? I hope this is clear. I think we'll discuss more if this is not clear, but we're systematically building it step by step as to why how the sequential systems have to be designed. So one way to fix this problem is to ensure that C allows update of Y only for a very, very small period of time, right? And if C is like a theoretical signal, like an ideal signal, then if you allow it for the time which is almost close to 0, which means that only when the C is going from 0 to 1, which you call as an edge, that's when you're going to allow this update on Y. Otherwise, in the rest of the times, you don't allow this update. So which means now you have pretty much solved, in theory, have solved the problem of the feedback and the race problem here. So if C is almost only when C is changing from briefly, and you allow the update only at that time, and this basically is the concept of edge triggering. So if you can build such a system where C is allowing update only briefly when it is changing from 0 to 1, in that brief interval, if you allow Y to be updated, you have an extremely reliable system where the race problem is almost eliminated. It's not 100% eliminated because finally this has to be built using a real system, a real device, and almost 0 is not possible there. We can keep it very small, but 0 is not possible. Edge is not possible, but it eliminates the race problem by a very large probability, right? I think if C is like a full, if C is active or inactive for a large percentage of time as it's changing, so you're only going to allow this transfer for this very brief period, which means the rest of the time it's completely blocking, and you have an extremely good sequential system. Y is updated when this small y is updated, and then you can clearly see the state of the Y. You can use it reliably at other places. And then when you want to update it again, you go back and see when it's changing. You allow small y to be updated, repeat the operation, hold the value. Again, this can be used reliably. The fact that the capital Y signal can be used reliably by using this means this becomes a very important piece to design a reliable digital system where race problems don't arise. There's another way. If let's say you don't have this, and you don't have a means of generating this this edge or a nearly zero delay type of transfer from small from capital Y to small y signals, then the other way is you still use the same previous circuit, which is where you are allowing the transfer happening only during the phase of the control signal. The first one is active when it's 1. So what you could do is you could use the same philosophy of blocking the transfer from Y to Y, but rather than blocking it from the signal going from Y to small y, you could actually break the loop by introducing another of a sequencing element, which is again active during a full phase of the signal, but the opposite phase of the previous sequencing element here. So if you can get this element to be active during the low phase of C, or C is equal to 0, now what that does is that when this is active, C is equal to 1, you would previously what you were seeing was this was rushing in and trying to update Y, and it would update Y, and this will keep happening. But now what this does is by introducing this sequencing of signal, you have broken that, which means Y cannot go back and update itself. So there is like a very clean operation. Y comes in, comes here, and then if Y is updating this small y, it continues to update because this is open. But the fact that this is breaking this path, this is sort of isolating the path from this output, this side to this side, which means once Y is stable and it's isolated, there is no more change possible on this Y. So you have a fixed value. And then once this closes, this opens up, we allow the output Y to be updated. And hence we have another means of ensuring a reliable sequencing from output back to input, and the race problem again is eliminated. So these two approaches are something which are fairly well known, and you obviously would have studied some of it, and people would have given some terminologies and names for those. But I wanted to give a very simplistic picture here so that you understand why these things come about. And finally, the whole idea of building a sequential system is that we need a sequencing mechanism to ensure the signals are reliable and they don't have a race problem, and we can use them in other parts of the complex system and and ensure that these results are then if they are stable, then they can be used to calculate other results which are also reliable, and then so on, and you can build a fairly complex system if the pieces of the complex system are all clean and don't have race issues. Right. So coming back, so the sequential elements that we have are in the digital domain are of three types. Now we sort of jumped from the previous slide here where I did not give them any names because I didn't want to put any names here because this is independent of giving them any names. We want to understand conceptually what they were trying to do. Now, once we understand this, let's try to relate to what you may have already studied. So there are three kinds of sequential systems. You have latches. We'll talk about what these are, flip-flops, and memories and bit cells. So memories, bit cells are another kind of storage elements, which has slightly more complexity compared to latches and flip-flops. We will not spend time in this presentation today. We're going to focus on the latches and flip-flops here. So coming back, so between these two views, this one and the one here, right? So which one do you think is in these views is a latch, and which one is a flip-flop? So if I go back, if I talk about, let's say this is this slide. So in this slide where I'm saying that C is allowing a Y to be updated when Y C is equal to 1. So what kind of a sequential element is it? Is it a latch or a flip-flop? Can you type here? Okay, I think we'll probably discuss this in the here. Let's quickly, there are a lot more items to cover. So the case when C is equal to 1 and it was updating Y, that's basically the case of a latch. And the other two cases where we had something called as an edge triggered operation or a nearly zero delay type of operation, or where we are blocking the flow by having two kinds of latch kind of elements, that was a flip-flop. So let's talk about it. So a latch, so this is a flip-flop, this is a latch. Okay, a latch, the black box view of it looks like this. You have a data input coming in, and Q bar is just a complement of this output. So what is the behavior? As we saw earlier, when the enable, so let's look at it. When the enable is high or the C is high, it allows Q to be updated directly by D. So Q is just following D, if you notice. But when enable is low, it blocks the path from D to Q. And nothing is coming in here. And again, when enable goes high, this is allowing this transfer to happen. So a latch is basically an element where, depending on the level of the control signal or enable signal, it creates a direct path between the input to the output. So we saw the case where this is still not very useful for triggered, or we need to have two sequencing operations and so on. So a flip-flop is basically that. I look at the three flip-flops here. So there's a data going to the inputs, the flip-flops, and there is this output Q. E is enable, or the control signal is this signal here. And so if you notice here, the value on the Q, let's look at QA and QB, is going to change only when based on the value, what the value on the data input is, when am I audible?
Yes, sir.
Okay. I think there was some refresh status, and then so if we build upon it, there's this concept of a synchronous system. Elements of the same type are updated together, and this control signal traditionally is called a clock. The name given to that is called a clock. I think, as you may have studied
Hello,
about
sir.
it in your
Arun sir, screen is not
Screen
visible
is not
actually.
visible, sir.
Screen is not visible, sir.
Okay, I don't know. This network issue is happening at my end, at other places as well. Is the network issue at my end, or it's happening at the organizer's end?
Sir, your voice is audible, sir, but you are not sharing the screen, sir.
Sir, once
Okay,
again,
I
please
think
share the screen, sir.
Yeah, sure. Looks like some network issue. I started sharing again.
Yes, sir. Now,
Yeah. Now it is visible.
it's visible. Yes, sir.
Okay. Did you were you able to see the previous slides where I talked about these sequential elements? Did we cover this? Were you able to see these? Were you able to see these slides, the earlier ones?
Yes, sir.
Okay, so that's good. So then let's quickly move on. So I talked about the synchronous system. Let's quickly let me repeat that. So a synchronous system is a system where what we are doing is we create a domain where a specific control signal sequences the update of the sequential elements in that domain. So all sequential elements of the same type are updated together in that domain. And so the traditional name given to this control signal is the clock, as you may have already learned about it. And clocks are usually generated from some reliable circuits, which sometimes are like PLLs or some DFLLs and so on. It could be coming in from crystal oscillators. And it's basically generated as a free running waveform and at a specific frequency and some specs for pulse width and duty cycle. So a very simple view of the clock waveform may look like this. It's a free running clock. It has a time period of T, and it's a digital signal. Boolean signal goes between logic low to logic high, and then which means there will be some voltage levels for logic 1 and logic 0 is basically ground. Right. So now if this is clear, let's sort of build upon this. So if we continue, how do we actually build this whole update is taking time. Yeah. So how do we actually build a latch circuit using logic elements or actual transistor devices? Now, one of the ways to build a latch, as we saw earlier, you need obviously require a feedback from the output back to the input, is to just take a multiplexer and so if you remember when I was discussing the control or the sequencing required using the control signal C, I said it almost becomes like an if-else statements. So which logic in our in our toolkit of logic as an if block. If this control signal clock is 0, it picks some value. If it's 1, it picks the other value, or so on. So if it is, let's say, a positive latch, which means it is allowing the Q value to be updated when the control signal value is 1. That means the value of input goes to the output. That's called a positive latch, and the circuit may look like this in a logical view of it. A multiplexer, and which overall looks like an if-else statements. If clock is equal to 1, D is equal to Q. If clock is equal to 0, Q is retaining itself. Right? And this is input. It should have been D. So Q retains itself. And if it's a complementary latch, which means it's a low latch or a negative latch, it has an opposite behavior. If clock is equal to 0, then it allows the Q to be updated by the input. If clock is equal to 1, it retains its value, the if-else behavior, right? Now, because it's a multiplexer, as you remembered yesterday when we were talking about it, we could build multiplexers using transmission gates. So which means if you start plugging in a basic multiplexer based scheme using pass gates, which looks like this, what I have done is in this, as shown in this diagram, is you have taken the output and you're feeding back to input on this side, and then you have the other branch of the multiplexer. This is a 2:1 multiplexer, right? As seen here, 2:1 multiplexer. So one input of the multiplexer is coming from its output. The other input is from the data input or the real input from outside. And you can build a latch using this scheme. This is a view of a positive latch. Now, if you're building an edge-triggered flip-flop, as we saw, one of the ways to do that was to ensure that if you remember the diagram that I showed earlier, I said one of the ways to ensure that the Y to Y transfer happens only for a very brief period, which almost behaving like an edge, and I could still use the same sequencing element using the signal C. And that kind of circuit to build is in reality usually very difficult. It's non-trivial. So the second approach of ensuring that Y to Y transfer does not happen is usually what's actually used, and to break the D to Q path and ensure the transfer happens only once at a specific point in time. But there, if you remember, we said we introduced two sequential elements. They were complementary. And that philosophy or approach is actually used to build a flip-flop or edge-triggered flip-flop. So this edge triggering is not happening because I have something special on the clock signal. Or the circuit is special here, but it's very simple because now I introduced two sequential elements which are latches, and the second one depends directly on the first to provide the input to it. So which means as soon as the first one is closed or blocked or opaque, the second one is only going to use what the first one has transferred. And therefore, this whole scheme from D to Q and the edge triggering, or the behavior which behaves like an edge triggered, is basically happening at the boundary when this latch is shutting down and this latch is opening up, right? And this combination is how people over the last few years have been using to build a flip-flop, which sometimes also called an edge-triggered flip-flop. In reality, this is not edge triggering because you have used two sequencing elements, which are latches, and you are breaking the path from D to Q by putting two latches here. But this does the job for us, even though it's not very efficient area-wise. We're going to talk about that later, but this is one of the most common approaches. And in fact, if you look at almost all the chips, all SoCs coming out over the last 20, 30 years, 99% of the flip-flops in the designs or sequential elements in the design, which are behaving like edge-triggered flip-flops, are built like this. This is an extremely reliable circuit, and people have been using this very heavily. And it's currently the dominant circuit which is used. No other variant of edge triggering based flip-flop is used in any design other than this one. So if you want to build this, just like we saw in the case of a latch, where you can use a multiplexer based scheme. So each latch is based on a multiplexer. Now you have two set of multiplexers. They work in a complementary way. So what you will have is you have one set of multiplexer here. So there's a branch on this side. There is another branch on this side, and then there's the output side of the multiplexer sitting on this side. So when you put them together, this whole scheme, we'll come back and discuss this in some detail during the break, and maybe try to understand the circuit if you have not seen this before. But this is a practical implementation of a flip-flop using these two latches. And this is called a master and a slave. Why master slave? Because the second latch is a slave because it only gets the value on its input, which is determined by the latch in the front. And as soon as that latch is closed, no new value can come in, which means its input is sort of slave to the output from the first. And it cannot, there's no other way for it to get any other new input. So it's sort of a very clean circuit. and this is called a master slave based edge triggered flip flop. So because it's actually now built using practical transistor elements, there are some sequential timing requirements. We're going to talk about that quickly. We'll come back and discuss this in more detail, maybe in the break, and maybe in a post break where we're going to have some more aspects covered. So the control signal, the clock signal may look like this when it is changing. Let's say going, it's a positive edge triggered flip flop going from low to high, right? And there is some requirement that the data on its D inputs should be stable before this change happens. This time for it to be stable is called a setup time. That means you have to set up the data before this change is happening, and you need to be ready before that happens. And then additionally, the fact that when you are changing the control signal for some time after the control signal has changed, you still want to ensure that that input data has not changed. Why? Because it's a practical real circuit. There are some real delays. There are some RC elements inside, which means you cannot just assume that the change in the output value happens instantly. It's going to take some time. So which means all these things are coming from practical engineering requirements, because you have transistors, you have wires, you have RC delays. So all of this requires you to ensure that you need to hold on to the data before the control signal arrives, and you also have to hold on to the same data for some amount of time additionally, so that the clean transfer happens from data to the output. So that's called a hold time. So after the signal, the clock control signal arrives, and you need to ensure the same data, it's called hold. The old value, hold the old value, and then set up the new value. That's the way sort of a mental model is. Hold is meant for the old value, setup is meant for the new value. If you want to write a new value into the output, you need to set it up some time in advance. If you want to ensure the output is retaining its value, you need to hold on. There's going to be some time from the point where the control signal arrives to the point where the output changes. This is basically almost like a combinational delay. Then this is called the clock to Q delay, or the output delay of the flop. So any questions here? Any questions? So let's see.
Excuse me, sir.
We'll come back to this. Let's take a break. I think it's going to be 8. We are running behind time today. So let's open it up to questions. You can type in the chat if you have any questions. Let's discuss the items so far recovered so far. Let's have some questions. Yeah. Please go ahead. Are you able to hear me? Yeah. Please type your questions if you have any. If you want any clarifications on the items that we discussed so far. Some of the. So Bhanu is asking which is more used, negative edge triggered or positive edge triggered. There is, in theory, there's no difference between the two. You could use either, but historically people have always used positive edge triggered, but there is no real difference between the two. So you could always use negative or positive, but just for the sake of familiarity and convention, people always use positive edge triggered flip flop, but negative is also used in a lot of places. And theoretically, there's no major difference between the two. Any other questions? Any other questions? If not, maybe we'll continue. Let's maybe spend. So how many different truth tables exist for Boolean functions of n variables? So that's a good question. So I assume when you say truth tables, you mean how many functions are possible? So there's this it's 2 power 2n number of functions that you can make out of it. Yeah, I think Savitri has written the answer. It is 2 power 2n, and so MOSFET inverter for a grid connected PV system for MATLAB software. So Rashi, can you unmute? And it's not clear to me what you're asking.
Sir, I am asking for that if we are using a MOSFET switch or a IGBT switch or any other gates also. So what are the differences of drain source voltages for the switches output and multi-stages? Like last day session, you described the stages of multi-stages, na? That's why I'm asking.
So what is the drain source voltage waveform?
Yes, sir.
The question is not clear. Are you asking, is there anything special about multi-stages, or are you asking how do we simulate it and so on? What's the question you have? What are you trying to ask?
Depends upon the multi-stages output for MOSFET, or matlab, which one is the best for it? If you are
You're always going to have multi-stage kind of digital logic because you can't build everything in a single stage. It's too big and too complex. And also we saw that you can never build in a CMOS single stage device, you can never build a non-inverting logic, which means if you want to build a non-inverting logic, you need to have at least 2 stages. So you obviously are going to have multi-stage implementation because of area, power, and implementation complexity reasons. That's fairly normal.
okay, sir.
So what's the difference between NMOS and pseudo NMOS? So NMOS is obviously just one kind of a transistor, as we saw yesterday. Pseudo NMOS is a logic style. It's a logic style which is slightly different than CMOS, where it's complementary, and as I showed yesterday, the pull-up and the pull-down networks are mutually exclusive. They don't conduct together or on together. Whereas in a pseudo NMOS, what's done is you have a pull-up which is also made of an NMOS device. But the NMOS device is not off. It is put in the resistive or the diode state, so which means it's always on, and therefore there'll always be a static current from or DC current from supply to ground, and it's actually not a very good circuit for building large scale systems. So pseudo NMOS was used till late 70s. After that, CMOS has completely replaced pseudo NMOS based digital logic styles.
Okay. There some MATLAB Simulink model.
Can you repeat your question?
Sir, can you share some model which are related to MOSFET or else other?
Yes, models are something which I'll see if I can share. Maybe you can send why don't you just send these questions to the organizers, and on the last day, I can take all these questions and try to put together some of these things. I don't have them right now, but it's possible for me to share what these models may look like. But these models are something which you cannot use in MATLAB. These models require you to run circuit simulation, which means you have to run SPICE. I hope you heard about SPICE.
Yes, sir.
So these models work only with SPICE.
Yes, sir.
So you should be able to run SPICE, which means you need to have the SPICE software installed in
Yes.
your labs or in your own computer. So these models may then be useful.
Okay.
These are models for the transistors.
Okay, sir. Thank you, sir.
Sure.
Excuse me, sir.
Yeah.
Sir, yesterday, last class did logical effort, na, sir.
Yes.
By taking the example of inverter. So you will written that PMOS will be the 2 and NMOS will be the 1. So depending upon the
Correct.
majority carriers.
The mobility
Sir,
of this thing. Yeah.
mobility carriers, charge carriers. Depending upon the mobility charge carriers, you written that PMOS will be the 2 and NMOS will be the 1, the value with respect to the parasitic capacitor. Sir, if suppose we take the example of NOR gate, sir. So we will connect that NMOS, PMOS will be the series manner and NMOS will be the parallel manner. So suppose if you connect
That's
the
correct.
PMOS will be the series manner, so we will add that capacitor, na, sir, 2 to 4, and we will write that
Which
NMOS will be the
uh,
hello.
So the capacitor you're talking about, the load capacitor should be on the load side, on the load.
Yeah, sir, I know that
On
the
the
capacitor
output.
always we will connect that the load side only, parasitic capacitor. But if you want to, I want to find that
Not the
logical effort.
no. Wait, hold on. Parasitic, it's not parasitic load capacitor. It is a load capacitor. Load capacitor
Okay.
means it's based on which gates you are driving, which wire you are driving. So it depends on. So let's say you're driving the same cell, then what is that load? It's that load we're talking about, not the parasitic load. Parasitic load is something which if you run a simulation, if you remember, I showed that y is equal to mx plus c type of line. That the value of c, which is that c value will capture the parasitic capacitance and the RC delay because of that. So the load that you have on the output should be a real load coming from the actual gates or actual wire connected there. Okay,
No, sir.
that's what that's the X.
Okay, sir, I'm not satisfied with your answer, sir.
Not satisfied with what?
I'm not satisfied with
Yeah,
your answer. Sir, my question will be that you want to find the electrical path, sir, logical effort path. Suppose we will take the example of one NOR gate or NAND gate, sir. We will connect that.
Correct.
Suppose take the example of NAND gate means we will connect that two PMOS will be the parallel manner, two NMOS will be the series manner. So PMOS
right.
means we will take the value will be the 2.
Correct.
NMOS will be the value will be the 1.
Right.
So with respect to connection,
And
so if you connect the two PMOS will be the parallel. NMOS will be the one.
NMOS will not be NMOS will not be 1 anymore because we have two NMOSs in series, which means to get the same effective resistance as an inverter, both the NMOSs now to have to become bigger, right?
Yes, sir. We will add
the
that one,
NMOS
sir. Whenever we are connecting the series manner, that time we will add, na, sir. The value will be there. Suppose we connect the NMOS will be the 2 means in series manner, we will add that one. Why exactly we are adding that?
The input capacitance that you are adding is on a specific pin, right? If you take a NAND gate, so NAND gate, let's say take A pin. The A pin, you look at the width that you assign to the PMOS, and you look at the width assigned to the NMOS.
Okay.
So if you take an inverter, the width of the PMOS you are given as 2 because you're saying the mobility of the PMOS is half the mobility of the NMOS.
Okay, sir.
So because you have mobility of the PMOS is half the mobility of the NMOS, you have to double the width of the PMOS.
Okay,
and
sir.
Therefore, PMOS width is 2, NMOS width is 1. So in the case of an inverter, the width, the input is proportional to 2 plus 1, which is 3, right?
So
and
in the case of NOR gate and NAND gate, sir?
Yeah, let's take the case of a NAND gate.
Okay.
In the case of a 2-input NAND gate, you have both the PMOSs in parallel, right?
Okay.
Both of them are sizes 2 and 2.
Okay, sir. Okay.
And the NMOSs are in series.
Series manner. We will take 2. We will add that 1 plus 1.
So no, we are not adding that 1 plus 1.
Okay.
You have to look at what is on the input. Which input is connected to the transistor? So A input is connected to the PMOS, and A input is also connected to the NMOS. So now what is the width? What is the width connected to the A pin in this case?
That will be the 1 only, sir.
No, it's not going to be 1, right? I think you're not understanding it. You probably have to. We'll discuss it, but I think your understanding is not clear. You're not adding the 2 transistors in series. You have to look at the A pin, one input of the A pin. Let's see if I can share that. But since we are out of time, let's see if I can quickly describe it. So this is what we are doing, right? So if you, I think your understanding was wrong.
Yes, sir. Yes.
You get it now?
Yes.
We are not adding these two. They are on
Okay.
two different pins. We are adding the PMOS and the NMOS. Look at each pin and look at the connection there. This 2 plus 2. This 2 plus 1. We are not adding 2 plus 2 here. We are not adding. This is not 1 plus 1 here. So you're looking at a pin and see what is the PMOS and NMOS connected. Is that okay?
Okay, sir. Finally, we will find the CO2. Okay.
Therefore, this is 4 by 3, and therefore this is 5 by 3.
Okay. So 3 will be the inverter. We will take previous value. We will take, no, sir.
That's your reference. That's
sir.
That's your reference. That's your reference. That's to normalize it.
Okay. Thanks, sir. Thanks.
Okay, so let's continue with. I think we still have a lot of material to cover. So let's continue with the section which is after the break. So we talked about here. We left it off here. We talked about some of these basic timing requirements for. Let me bring it up in presentation mode. So we talked about this timing requirements for the sequential elements, the flip-flop specifically. We talked about setup, which means for new data, you need to set it up before the control signal or the clock signal arrives. And hold is you want to retain the old data on the output, which means you have to hold on to the data on the input. And that hold is this. So both setup and hold are with respect to the input and the clock. So between the clock and the output, it's called the output delay or the clock to Q delay. Clock to Q because clock to the Q pin, that delay, and that basically is like an output delay. After the time when the clock arrives, to the time when the output changes, 50-50 as we discussed yesterday, 50% transition to 50% transition point. That delay is called the output delay or the clock to Q delay. So there are some waveforms. I think once I share the slide, you can take a look here. We'll skip this. Also skip this. Okay, so let's talk about how do we simulate or characterize sequential elements. I'm going to spend some time on this paper today. I've taken some diagrams or figures from that paper. This is a very a good reference to understand about flip-flops and latches and how to simulate them, how to understand their behavior. So if you have to create a test bench to simulate a flip-flop, it may look something like this. So if you notice here, there is a flip-flop cell or a circuit. It has these pins, T pin or the input pin, Q pin or the output pin. Sometimes we also have a complementary version of an output pin or the inverted version. And then there's a control signal, that's a clock signal. And these are the major pins of the this flip-flop. Now, what we're doing is we have plugged or connected some load on the output. This load is representing what gates or what wire I'm going to drive or drive from the output of this flip-flop. That means there could be some logic gate sitting in here, which needs to be driven. So there'll be some gate loads and some wire loads taking it from this to this. That's this load. And then on the input side, there could be some inputs coming in from some other logic gates, and I need to probably buffer them or change their transitions or control the transitions. Transition means, as we discussed yesterday, transition time means the rise time or the fall time or the slew, as sometimes people call it. So we have that. I can add some capacitance here to control what is the transition, how it varies when it's being driven from this side. And then there is this set of inverters or buffers that we added to drive the clock pin of this. Now, in the simulation of a flip-flop, let's look at the plot. What's usually done is, if you notice the x-axis is being called D to clock delay, and the y-axis is basically this is the output delay, or this basically this is both the units are in time. In this case, they are picoseconds, and so the x-axis specifically is capturing the relative arrival time of data with respect to clock. Relative arrival time in the sense that the clock edge is arriving at a specific point in time. And so if we go back to this view, so this is the clock edge. With respect to this, data is arriving. It can arrive early or it can arrive late. So this relative arrival time is being called D2 clock. That means how early is data with respect to clock. So we go back to this plot. This x-axis is basically that time, relative time between data to clock. And then we are getting the data to arrive very early or very close or later than the clock. So if you notice here, when the data is very early, you're going to be far on the right on the x-axis. And as it approaches the data, the clock, you are coming towards 0 because the relative time is now almost same, which means the difference is 0. And then if the data is later than the clock, it could be coming in negative and so on, right? So when you do that, basically what you're doing is you're changing the setup time of the flop and as it's changing. So you're continuously varying when the data is arriving, whether the clock can capture the data or not, and you're seeing the effect on the output of the flip-flop. And you plot this waveform. When you run the simulation, let's say the data is coming in at 100 picoseconds, because the unit is picoseconds. 100 picoseconds, you check what is the delay from the clock to the queue, the output delay. And you see that the delay is roughly around 70. Okay, let's do this. Let's make it 80 picoseconds. Let's check the delay. It's around 270. I keep repeating it. I come till almost 40 picoseconds and I see the delay is almost 270. And then I come to 20, the delay is slightly increased. It's around 275 or 280. And I keep repeating it for multiple data points. I push the data now close to 0, which means data and the clock arrival time is exactly same. And I see that the delay has increased from 270 from the initial values to now 290. I push it further, till a point where the flop actually fails to capture. Why? Because the flop shuts down. It's a flip-flop, right? As we saw, it has an edge-triggered behavior, which means if the data comes too late, it will not be able to capture the reading. So this curve, where you're looking at the output delay or the clock to queue delay, as the data arrival time is changing with respect to clock, is a very important figure of merit for a flip-flop. It's something which you will I'll describe in more detail. This is something what's used for the characterization of the flip-flop, and something which you can run at your end as well. When if you have a flip-flop or if you build a flip-flop in a circuit, you can run some simulations. You can exactly replicate this kind of a curve at your end also. All flip-flops show this behavior. The behavior may not exactly be something like this, but depending on the type of flip-flop, you could have a behavior where it starts failing quickly, could start failing later, but it's going to have a period where clock to queue is a constant, and then clock to queue is slightly increasing, then increasing quickly, and then it fails to capture. So as shown in this plot, so this curve, which I'm highlighting here, or sort of tracking here, right? Now, there is a stable region. The stable region is when the clock to queue value is almost fixed. And the output delay of the flash or the flip-flop is constant, is almost fixed, around 270. And then there's a metastable region where the output delay is getting affected because the data is coming closer and closer to the flop. And then there is a portion where the flip-flop actually fails to capture. There's a failure portion. That means the flop has shut down. It cannot capture anymore. That's a failure point. So this is for the output of the clock to queue. And then you can also plot it with respect to data in arc or a output you can track. So data to queue in the case of a flip-flop will be nothing but data to clock delay plus the clock to out delay, clock to queue delay. So when you plot that, you may have a curve which looks like this. When the clock to queue is a constant, you have a linear behavior, which is directly of 1, directly tracking the x-axis. As input is changing, it's exactly changing. So slope of 1, and then as soon as it enters the metastable region, the clock to queue starts increasing. The slope is now coming down, 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 less than 1, and then it becomes 0 around this, and then here slope starts increasing. That means the T2Q is increasing because the clock to Q is increasing, and then the flop fails to capture. So this is an extremely important figure of merit for flip-flops and also latches. Latches may have slightly different behavior, but the approach to simulate flip-flops and latches are very similar. And we'll probably discuss this in the during the break if you have any questions. But this is something which probably, if you have a simulation setup at your end, you should try to run when I share the paper, and you can report it maybe on the last day what your observations were. And if you have any doubts, we can discuss that in more detail. Now, what are some of the careabouts for designing sequential elements, latches or flip-flops, right? We saw the timing aspects. Why timing aspects are important? The timing aspect is important because the timing aspects of the flip-flops and latches determine the performance or the speed at which we can run the system, the digital system. You may have heard about Intel CPUs or AMD CPUs, Qualcomm Android-based CPUs running at 3 gigahertz or 2.5 gigahertz. The recent Intel and AMD CPUs are running even 5.5 gigahertz. 5.5 gigahertz, we're talking about extremely fast systems. When you start pushing the performance to higher and higher gigahertz, the flip-flops and the latches become extremely important because their setup time, hold times, clock to queues start becoming a big percentage of the clock cycle time. So when we say 5 gigahertz, it is nothing but the frequency of the clock signal. The clock signal, as we saw earlier here, this time period, this clock is running at 5 gigahertz, means this time period is 1 by 5 gigahertz, which means this time is 200 picoseconds, which is significantly small amount of time. That's an extremely fast system. So if you want to be able to run that fast, your flip-flops and the latches should have extremely small setup times, clock to queues, and the hold time should not be too big, and so on. Okay, so which means the timing aspects of these flip-flops and latches are extremely important. Setup, clock to queue are meant for performance, which means they have an influence on performance. So the bigger the setup time, they have a bigger impact on performance. You cannot speed up the clock if the setup time is large. Clock to queue is large, setup time will be limited because of this. So when I say performance, I mean the clock rate, 5 gigahertz, 2.5 gigahertz, 3 gigahertz. It's basically that. Hold time is more has more of an impact on the robustness or the reliability or the functional aspects of the digital system. If the hold time is large, it may have an impact on the way we may have some functional issues with the in the digital system. So if this becomes too large, then we may have a problem. So we should keep it small. So this again has an impact, not on performance, but indirectly on a performance, not directly on performance, but directly on robustness and reliability and functionality. Again, area is important. All digital circuits, sequential circuits, in any circuit that you're building on chip, area is extremely important. That goes without saying. It's a basic factor. When we keep talking about PPA, as you may have heard some of the people from the industry talk about, PPA stands for power, performance, and area. So PPA metrics, people say that means the constraints are power, performance, and area. So I talked about performance. When I say timing aspect, it means performance. So which means the P out of the PPA, 1P is covered here. A, area, has to be extremely efficient for the, or I should be getting extremely high performance out of this circuit. If I want to spend a lot more area, I need to be getting a huge performance improvement using the circuits. So the trade-off should be really good. Otherwise, if the performance is not good, I want the area to be small. Again, the other P is for power. So clock power is extremely important. Clock, for example, if it's a 3 gigahertz, 4 gigahertz, 5 gigahertz clock, which means clock is switching at an extremely fast rate, which means we sort of know that the power of a digital system is sort of dependent on the clock frequency linearly, directly dependent on that. So F increases, power increases, right, at the same rate, then the same proportion. So which means clock power, if it's high, I have a problem because my design is running fast. If my clock power is large, in the sequential element is large, I need fast to either the circuit is not very efficient for me. data power. What does data power mean? Data power means that if, let's say, the sequential circuit is not switching, that means clock is not coming in, or so I don't want it to consume power when the data is changing, or it should be very small. So again, both these metrics are related to power. I haven't talked about leakage. So leakage power again is an important metric, and so along with clock power, both these powers, clock power and data power, are dynamic power, which means only when the circuit switches you have a power consumption. Leakage power is more like a static power. It's always going to be draining out the supply, but it's a very small value compared to the dynamic power. But it is also very important because if there are millions of flops or sequential elements like flip-flop latches in the design, that's a big amount of leakage power. Another very important metric, usually not discussed when you study in your colleges and also in the academia in general, is the aspect of robustness and yield. The circuits that you're building need to be extremely robust and should yield, which means on silicon, we should get these circuits to work with with very minimal trouble. They should always be functional or nearly always be functional. If they are not, even if the circuit, let's say, seems very efficient in terms of area, power, and timing, but let's say on silicon, if it has potential robustness or yield issues, it's a no-no. I think people will just say, okay, I'm willing to pay extra area and power, because why? If you remember the first day's presentation, I talked about that the ASIC and the FPGA fabrication costs are going up. So which means if I build a chip and I fabricate it, I get the silicon back, I verify and test and verify it, I find that my sequential circuits are not working because of some problem, then what it means is I have to go back and design the whole thing all over again and spend nearly what 10 million to 30-40 million dollars again to fabricate the chip, because I have to waste my engineers' time on it. I have to go back and fabricate, go to TSMC or Global Foundries or UMC on these foundries, fabricate the chip again, test it again, verify again. The whole process is pretty expensive. So which means I better have a circuit which is extremely robust and yields well. So this is now becoming one of the most important factors with respect to designing of complex circuits like sequential elements. And again, verification complexity is also very important. When I say verification complexity, it means that the way the circuit behaves and the way its timing aspects are understood should be something we should be able to simulate and verify before the product is taped out, or the silicon it goes to the foundry for fabrication. The database goes to the foundry for fabrication. So verification complexity is also very important. Certain circuits sometimes have some complex behavior which is not very easy to verify, and therefore they may show have some robustness and yield issues. So therefore you would like to ensure the circuits that you have very clear functional and timing models, which you can then run either circuit simulations, or you can you do some Verilog simulations to capture the behavior. Otherwise, we would like to avoid it. So we'll talk about this. These are some, usually these aspects are not covered when you read in textbooks, but this is completely coming from because I spent time in the industry, and this is a lot of industry people who would vouch for it, that these are some of the very important factors which limit the kind of sequential elements that we can use in the on silicon these days. Historically, like 20 years back, 30 years back, a lot of very different kind of flip-flop circuits were used. I'm going to talk about some of those circuits today, not in detail, but just to introduce you to some of them. And those circuits look very promising when you look at them from a PPA point of view. But when you actually go to silicon, you would find that they are yielding very poorly, or they have very complex verification requirements or test requirements. So therefore, those circuits are not used anymore, even though you may see them in the textbooks. So let's talk about some interesting flip-flop topologies. So I have 3 of them here. So Ravi Kumar raised his hand. Not sure why. We'll cover that in the break. So I have 3 flip-flop topologies here. So figure 1, this one is basically a master-slave flip-flop, as we saw earlier. 2 latches put back to back so that this whole thing behaves like an edge-triggered flip-flop. It's a master and a slave flip-flop, a very basic master slave flip-flop. Then this is figure 2 is another master slave edge triggered flip-flop. But what I have done here is this is a single bit master slave flip-flop. Why single bit? Because there's only one D input and there's only one Q output. So Q and D are only 1 and 1. So therefore, this is a single bit, a regular flip-flop. And here, what we're doing is we have built a multi-bit flip-flop. Multi-bit flip-flop, what the benefits, I'll come to that in the coming slides. So here, what I've done is I've taken 4 of these single bit master slave flip-flops, put them together. Now I have 4 inputs, if you notice, D0 to D3, and then I also have 4 outputs, Q0 to Q3. I haven't shown them here, but they will have Q4 outputs, and so on. So this is called a multi-bit flip-flop, but again based on a master slave approach. The third one is one of the most interesting circuits, which I think you may see that in textbooks. This is called a pulse latch. A pulse latch, in theory, is the ideal edge triggered circuit. What you have is here is a latch, and you have a clock signal where you have some circuitry which is called a pulse generator, and that goes in and it goes into the latch and generates an output based on the input. So we'll talk about this. So these are 3 topologies we're going to talk about. Let's cover them one by one. So I talked about the first one. I gave some introduction to it. This is the regular master slave flip-flop. What are some of its characteristics, the salient features? Extremely good hold time. Why extremely good hold time? What does hold time mean? The other way to say what is a hold time, other name for hold time, is nothing but race or the race problem. So if you have a hold time, means you have a race problem. So as we were discussing in the first few slides, I try to sort of clearly show why race is a problem in sequential systems and how we need to mitigate that. So if a flip-flop has very good hold time, means it is very good at avoiding hold time problems or race problems. And that's because you have a master and a slave. The slave only gets an output if the master allows it, and that's at the edge of the clock. And therefore, it has a very good hold time because of the master, which is sitting in the front, which is operating on a different clock face. Its clock to Q can be small to large to medium. It's fairly good. Now let's look at the clock power, the dynamic clock power. Now, if you notice, there are a lot of circuits in the clock path. There's a clock pin here, and then there is a buffer here, 2 inverters. Then this is going and controlling the switching of these gates here, these pass gates here. Basically, these are multiplexers. So there's a lot of load on the clock net. Clock B, clock BB, clock BB going to so many places. Therefore, the clock power is high. And additionally, the clock power is being consumed even if there is no change in the output, which means if the data is not changing and you don't expect output to change because data is fixed, even then clock power is being consumed. Therefore, this is a fairly inefficient from a clock power point of view. It has large area because there are 2 latches and all these additional clocking related ones, these controls, but you can usually build it in a fairly compact layout. And this is something which is heavily used in the industry. And most of the flip-flops, I said 99% of the flip-flops in the designs are master slave flip-flop. So there is a way to make it more efficient, specifically from a area slightly and significantly from a clock power point of view. So if you notice, each one flip-flop is going to have this buffer. So which means every flip-flop has to pay this penalty of the buffer power, because 2 inverters are here. Now, what if I actually share this over multiple flip-flops? And that's what this multi-bit flip-flop is. I can bring this from this picture, I can bring these 2 buffers out, and I can share them across this, which means the cost of this buffer and its switching power can now be shared by these 4, which means in theory, the clock power of a multi-bit 4-bit flip-flop is going to be very sort of, it's going to be a lot more efficient. And the power of this is going to be shared, which means it's 1/4, and then the additional power is only coming from the switching of these internal nets of the latch. So this makes it more efficient. And because you all also brought this circuit, which is shared between the 4 flops, it sort of reduces the area a bit. and other benefits of the multi-bit flip-flop are similar to the single bit flip-flop because the underlying circuit is still the same. So which means because it's a master slave, you're going to have a very good hold time. It's more area efficient, as I said, because you brought this clock circuit out. It's got very good dynamic clock power, better than the single bit because you're sharing it across now four flops now. But you still have the problem that when the data is not switching, you still have clock power being consumed, but it is less than the previous case. A compact layout is possible, and you can build these clusters and make it more efficient by sharing this clocking circuitry across more than 4 flops. You can have 8, and I have seen cases where people have used going up to even 8 flops being shared. So basically, it can be a 8-bit master slave flip flop. So let's come to the pulse latch or a pulse flip flop. So these two terminologies are interchangeable, which means the same circuit could be called a pulsed latch. There's a latch and you provide it a pulse. And sometimes people call it a pulsed flip-flop. And this can be confusing here, but people in the industry can use these two names interchangeably. They mean the same circuit or same kind of circuit. So what do you have here? There's a latch, and I've shown a latch cluster, which means it's a multi-bit. But in principle, you have a latch, and you need a circuit called a pulse generator. Why do you need this circuit, and why can't you just have a latch? Because as we saw earlier, just using a latch prevents the race only when the clock is 0. When the clock is 1, you still have a race problem or a hold problem. So therefore, what is done here is that you want to control and you want to introduce an edge triggered kind of behavior, and therefore what's done is that you take the clock and you change its pulse width or duty cycle using this pulse generation circuit, so that you have a very small window in which the latch is transparent. So the period when the clock is 1 and the latch is transparent and allowing the race to happen is minimized significantly because of this circuit, and therefore this now behaves like an edge triggered circuit. And here you built a cluster because you want to share the area and the power overhead of this pulse generator across multiple bits, as we saw in this multi-bit master slave flip-flop. Same concept. This is a cluster, which means you can share this pulse generator power across these multiple bits to make it more efficient. And that's what is being done here. So what are the salient features of this circuit? Extremely good setup time, very good clock to queue. It's comparable to the master slave. And there are some additional benefits. I'll skip that because you may not completely get it, but there's something called as it can give you additional performance advantage because of it can recover something called clock uncertainty. You can hide the jitter and so on. And the hold time of this circuit is extremely bad compared to a master slave flip-flop. And the clock power savings is much better. Why? Because previously in a master slave, you require a master and a slave, 2 latches, right? As we saw earlier. Whereas now you only need a latch, and there's only a single latch. And also the clock power of the pulse generator is now being shared over a multi-bit latch cluster. So there's an efficiency part there. So it has much lower clock power, switching clock powers were switching compared to a master slave based single bit master slave or a multi-bit master slave flip-flop. Compact layouts are possible, and I have seen clusters being built from 4-bit going up to 16 bits. But what is the problem with this circuit? This seems like an extremely area efficient and power efficient circuit, but what is the problem? The problem with this circuit is it is extremely sensitive on silicon, and a lot of silicon failures and yield issues are seen. That's one of the reasons why people have almost given up using these circuits, even though in theory and in the literature or in textbooks, you may see that this is an extremely good circuit, but in reality, this circuit is very sensitive and difficult to make it work on silicon. So industry has almost given up using these circuits, and very few chips would actually be using these circuits anymore. Okay, I think so. So I covered this. I gave you a sort of a brief introduction of some of the circuit topologies for flip-flops. Let's quickly talk about this paper that I want you to read. This paper, you can probably take a note. So this is written by these two authors, and it's called the comparative analysis of master slave flip-flops and latches for high performance and low power systems. So this paper gives a very good introduction of how to simulate these flip-flops and latches to compare them. You may have different, you may read some papers or you may read some flip-flop circuits from your textbooks. Let's say Rabe or Harris or one of these textbooks that you may be having. And let's say if you want to compare them by yourself. So this paper allows you to, or introduces you how to set up the simulations, how to run simulations, how to analyze the results, and so on. So I would urge you to, if you're interested in learning more about flip-flop circuits, latches, the circuit aspects, the timing aspects, performance aspects, power aspects, then I would suggest you go ahead and read this circuit. I think if there are questions specific to this paper, I will discuss that in the break. Maybe I can even bring up this paper. I have that open in my browser, and we can discuss that. So we're nearing the end of today's session. I think that's mainly it for today. Let's open up for questions. Yeah, please go ahead with your questions. So in case you want me to bring up the paper now, please type a yes. If there are a good number of people who are interested in me covering that paper, I can bring it up if there are no questions to ask. So I see Savitri saying yes. Are others interested? Do we have more interest from the audience? Do we have any questions? Let's feel free to type in the chat. And if you have any questions, please maybe if you want to ask directly, please go ahead. I see three responses for sharing the papers. If I see around 10, I will start sharing the paper. I need a few more. Maybe I will wait for 2 more minutes. If there are no more questions, maybe I'll just start discussing the paper.
Arun, sir.
Hi, your voice seems to be breaking.
Sir, we are having two types of logic now, sir. Positive logic and the negative logic. Am I audible,
right.
sir?
Yeah, I can hear you.
Yeah. Sir, two types of logic are there. Positive logic and the negative logic. Hello?
Yeah. When you say positive logic and negative logic, I assume you mean the rise edge or a fall edge type of.
Yes. But usually we go for the positive logic and any examples where we are going to use the negative logic?
So negative logic, I mean, there's nothing, even though it's called negative logic, there's nothing very different about it. So specifically for the audience, when we say negative logic or positive logic, we are referring here to a sequential system or a digital system which is sequential, where you have the sequential elements either operating on the rise edge. That means when the clock signal is going from low to high, 0 to 1. And if it's a negative logic, we're saying the clock signal is going from 1 to 0, right? It gets triggered at the time. So in theory, there is no difference between the two, but just because of convention, people use the positive. But where your question is, where do we use negative? So there could be cases. For example, let's take an example. So let's say you have a DDR. So you may have heard about DDR chips. Have you heard of it? Yeah, DDR memories you must have heard of, right? So DDR memory is basically, DDR stands for double data rate. So when it's a double data rate, it means that you are operating on not just the on one edge of the clock, you are operating on both edges of the clock. You're double, you're trying to run transfer data at both the edges of the clock. When transferring data on both the edges of the clock, you need to be active on the rise edge. That means positive level as well as a negative level. So in such cases, very frequently, the negative flip-flops will be required. There are other places also. For example, there is this something called as a half cycle path. A half cycle path means data is going from a positive flop to a negative flop. You again would require a negative flop because you want to transfer data from a rise edge to a fall edge. So there are such places where a lot of negative edge triggered flip flops are being used. Okay, so I see. Are there any more questions? Otherwise, I'll probably start the paper. I see more than 10 yeses, so let's maybe cover the paper. You can always come back if you have any questions. So I think I had it here. So this is the paper I was talking about. So I have it open at my end. So if you look through it, so obviously you may have seen IEEE papers. So here, if it's a standard IEEE paper, you will have an abstract section where you would have a brief summary or a high level of what the paper is trying to do, or trying to describe, and what they have accomplished in the paper, and it talks about it. So a set of rules consistent for estimating real performance and power features of flip-flops and latches, right? And then new simulation and optimization approaches presented. This is something which I think if people are interested, it will be like a good thing to understand, and targeting both high performance and power constraint or power budget systems issues. The analysis approach reveals that the source of performance and power bottlenecks. Bottlenecks means constraints or limitations in the different styles in 99. So it's been a good amount of time since this has been published, and it's very frequently referred by people who want to understand about flip-flops and latches and understand how to build the circuit, how to characterize them. I personally have read this paper many times, frequently, and I sort of clearly can confirm that this is a very good reference for you to sort of get started with. There will be a lot of things which may be new to you. So one of the ways to read the paper is to read through it quickly, high level, see what are the major things that they're going to talk about, they're trying to cover, and see if there is something which catches your attention, which you understand, and quickly read through it, see what you understand. If the whole paper seems confusing or it's not very clear, there are a lot of concepts which you don't understand, then that's okay. That's quite normal for a lot of us. Then what you do is go to the references and start reading, see if there is any paper reference which seem intuitive or easy for you to understand. Maybe you can start picking that if this paper seems complex, and look through some of the references and then try to read those and repeat the same exercise. The exercise is the same. Quickly go to the abstract. Abstract will be fairly easy to understand. There's no technical details there. It's written in simple language. And what the paper accomplishes is described. So read through it, look through the introduction. Introduction is a good section because not a lot of technical details are given there. What is the state of the art? State of the art means what is currently the best approaches being used. That's described. And then look through, again, as I said, any portion which is catching your attention, which you understand or which seems interesting to you, read that. and then go to the references, repeat it. That's the way. It's going to be a slow process, but it's a very sure process. It works, but that's what I have done. And it worked for me, and it still works for me. There are a lot of new areas which keep coming up. I may not know everything, but I'm going to be patient because I know that I will not understand everything. But if I give myself time, and if I'm going to give myself time, let's say I give myself even 2 weeks to understand a paper, I'm pretty sure that in the 2 weeks I will easily be able to understand, even if I didn't know at the start. By the time it's end of 2 weeks and I'm reading the paper, let's say an hour or 2 hours every day, I should be able to get it by the end of 2 weeks, at least 25 to 50% of it, if not completely. And then you can probably bookmark the paper and then find the interesting references, go to those references, or read about some of it from the textbook, which you may not know. And then maybe a month later, come back and read the paper, and you will realize that you will probably understand it even better, and you will be able to understand the whole paper. And you can even start running some of the analysis or the designs that the paper is being talking about. So that's going to be a systematic approach which you should follow. And don't expect others to just go and explain to you, because this whole process of understanding is a very slow and individual process. Even though I am trying to give a talk and explaining things, I'm able to explain it because I understand it and I spend time on it. And just because I have explained it, let's say fairly okay or well, doesn't mean that you understand it till you actually try it out at your end. So that's very important. The whole learning process is not something which can be passed to the audience in one sitting. The audience, as individuals, you will have to probably put the effort to and be patient with yourself. And that's the only input I can give you. As long as you're patient and you have a systematic way of reading these papers, as I described, I think all these things can be understood in gradually. And I think once you have some basic understanding, the whole thing keeps compounding, keeps becoming faster, because now you understand it, you can read some more papers, from that you will learn more, and this whole process keeps repeating. And this is like a compound interest, right? This whole thing requires you to start putting in an effort now and understand some of the basics. A lot of these papers are very interesting, and you can go to the references, find some new papers. So let's come back to this paper. As I said, it talks about how to run simulations. As I said, here I showed this plot, right? So it shows, where is it? I think it was somewhere here. Let's see. So it talks about these curves. I showed these curves to you. So maybe read this again to understand them. And it shows these curves for different kinds of the flop circuits that's been discussed later. I didn't cover all the flop circuits, but you can sort of read through them. And if you have any questions, we can probably discuss them on the last day. For example, this is a regular master slave flip-flop, and it's power simulations, power versus sizing, power versus transistor width is being compared. I'll talk about this power delay metric maybe tomorrow when we talk about optimization and timing trade-offs and so on. But it'll be good for you to read this. The test bench, the simulation, this is what I was talking about, how to set up the simulation. That's shown here. I took this from this paper. So read through this. It shows how the simulation is to be run. And it's described in good level of detail. How the transistor sizing could be done for performance or power reasons, that's all described. And these are the different flip-flop circuit styles, circuit topologies which are being covered. A good number of them are being covered. A lot of them are historic and not really relevant anymore. But this is a 1999 paper, which means a lot of them were recent at that point in time. For example, I'll tell you the flip-flops which are still active and use. PowerPC 603 is a master slave kind of flip-flop. It is still something which is heavily being used. All these ones, HLFF, HDFF, are not relevant anymore. These are based on pulse latches. And then a lot of the other ones again are irrelevant, but it will be good for you to not worry about the circuit styles, but specifically try to look at how the analysis is being done, how the simulation is being set up, because we'll always keep having newer and newer or different flop circuits and flop topologies coming up from the textbooks, or you may sort of design yourself, or you may make some minor changes to the circuits to see the effect of that. So you need to know how to simulate, how to analyze, how to compare. That's discussed in very good detail in this paper, and that's what should be the takeaway from this paper. Okay, I
Arun
think that's
sir,
what.
Arun sir, I have one question.
Yes, sir.
Yeah, sir, because when we go for a paper, we have to compare our result with any one of the previous paper. Correct, no, sir?
Yeah, this
Hello?
paper is this paper. It all depends, sir. It depends on what you're trying to do. This paper is not really
No, sir. What
designed.
I'm asking, whenever we are comparing because we have to prove ourselves that we are done a better than the previous work. We have to compare and we have to show the betterment compared to the previous papers. So when we taken any reference paper, if they are worked in a tool like a cadence tool or anything for calculation of area, power delay and all, again here also we have to work in the same tool, no? Because when we are comparing, the data should be in the same tool.
No, it doesn't need to be, because it depends on how you are comparing. So for example, if you can compare in terms of, let's say, schematic, the number of transistors that you have, that doesn't matter which tool you use, right? For example, you can say my circuit has.
Suppose power, sir. If you go for any other tool, the power calculation will be in the different way. If you go for either it is yeah.
Even that can be resolved that can be managed by you. For example, let's say you have tool limitations. You can write that in the paper that you had a different tool than that was used in that paper. So you are comparing power in your own way. So how do you compare power in your own way? For example, you can say that the transistors used on this net is so much, its width is so much. That means the total, as we saw in the logical effort exercise, if you remember, we were saying that the input capacitance is going to be based on the width of the thing. You can say the load on this net is going to be so many widths, and then you can repeat the exercise for all the nets, and you can cover all the nets, which means without even running simulations, you can approximately say the power is going to be proportional to the sum of all the widths that you have calculated. Now, again, this is completely tool independent. So it all boils down to whether you want to use the fact that you don't have the tool as a limitation, or you still want to go ahead and do it. So it all boils down to that. I know that you need tools, but if you are, unfortunately, let's say we are limited because of it, people have done work where they have ways of comparing it. So maybe it cannot go to a very top-notch conference paper or top-notch journal, but it can go to a sort of a lower level or a mid-level journal.
At least
or mid-level
Q4 general, Q4 journal we can publish for, sir.
Yeah, something can be good. So that could be a starting point. So once you have that, then, and also I think there are a lot of open source simulation tools. I think you talked about introducing the audience to that. I'll try to cover that on the last day. If you can just maybe capture some of that in the notes and send it to me, maybe tomorrow, I can add this to my agenda for the last day, where I can cover some open source tools, for example, open source Spice, open source PD tools, which are now available, not used by the industry. So I don't use them, but I know that they are available, and I can expose the audience to that, and they can start looking at it. So if you can just capture some of these items in the agenda, then send it to the organizer and mail it to me, I can try to document that and send it and share it to the audience over the coming days.
Okay, sir. Thank you, sir. Thank you.
Okay, any other questions? So let's see, we have Veena asking, if we go through the reference papers, can we understand the paper? As I said, it will take some time, but yes, you can gradually should be able to learn it and understand. But obviously, it all requires you to have some basic foundations. Let's say you don't even know that the formula for CMOS power is CV square F, and then you are confused where the formula is coming from. In such cases, obviously, you are going to have a problem because you don't even have a good foundation. So it's important to have some decent foundation where you're comfortable with what's there in your textbook. And then over and above that, you can build upon these papers. So first thing is foundation, and be sure that you understand all those things well in what's there in the textbook. And then you can start working on these papers and start doing projects. Any open source simulation tools? Yes, there are a lot of open source simulations tools. Even if actually go do you Google search, you can get it. Maybe I can try to cover some of it on the last day. So we have, it's 9 o'clock. We'll end it here, and maybe I can take a couple more questions if there are any. Otherwise, we'll end it in the next 2 minutes. Yeah, if you have any questions, please feel free to ask. All right, thanks a lot. Thank you all, and we'll meet tomorrow. Bye.
Yes, sir. Thank you, sir. It was very informative session. Thank you, sir. And thanks to all
Okay,
the
thank you.
participants. We will meet tomorrow. Thank you. Thank you, Atal.
Thank you. Bye.
Thank you. Thank you.